More on cellular automata. Automata to automata. Wolfram. New kind of science! Okay. First of all, I might as well say this goes really deep in the history of me now. It's decades and decades, 30 years maybe, or some crazy thing, that I've had an interest in this. The game of life. You want to know about these things? The game of life. Okay, Wolfram Cellular Automata. And if you ask me, fractals. It's this strange patterns, but also lack of patterns. Like in Rule 30, you've got these triangles. There's definitely a pattern to it that you could recognize and print out. But it's got this chaotic nature to it. Okay. Now, what they all have in common is recursion. Okay, because that's the thing. So this two-dimensional picture of the Rule 30, triangle, given the standard initial conditions, this two-dimensional picture, it's a one-dimensional cellular automata. It's one line, right? That's over time. You're seeing a chart over time when you see that whole shape. You're seeing its evolution over time, right? Life is a two-dimensional one. You usually just watch one frame as it changes. Really, you could plot that out in 3 dimensions and see the same kind of structure, right? So, so the recursion is that it takes that first line, processes it, and then it has output. And then it takes that output and processes it. It's basically a function. Recursive function is a function that calls itself. So you call it with the one pixel in the middle, and it just calls it transforms that itself and calls itself uh, again with that output, and it goes down as deep as you want. And they do 250 generations, then it goes down 250 generations. By design, it would go infinitely forever, right? And the thing you would get back would be that final row, however meant that row of that generation, right? So now the method is really easy. Anybody could have explained to them, as well as with certain kinds of fractals, how to create them. Okay. And the cellular automata are particularly simple, right? Anybody could be, you could just give them a bunch of blocks with white and black, or tiles with white and black sides, give them these 8 rules, and they could execute that thing, right? Just a matter of time, and they could execute it. Slower than a computer, but they could execute it. Pretty simple. As a matter of fact, I was thinking about it. Could you make a machine that wasn't based on logic gates? And I say this because logic gates depend on quantum mechanics. So could you do it just with the Newtonian, Jules Verne era type machine? In theory. Well, I think you could. I was thinking you could have a machine that goes over 3 blocks at a time, presses against blocks so that the dark ones and the light ones are different sizes, presses against, gets the impression, goes over to the key, locks those blocks in place so they can't slide anymore, tries to press against the thing. If it gets in far enough to click a switch, because it'll only fit the exact shape, then a white or black ball or tile, depending on the rule, falls in and can be taken over and put in the next slot, all by clicking down and doing things all very mechanically. So you have a mechanical process, right? Very simple mechanical process, simple to understand, simple to build a machine, to automate, and yet it leads to this chaotic, unpredictable pattern. If to me, as I said, that just says that no matter, uh, well, okay, apply that to real life. Real life is a recursive function. So we know that very simple mechanical processes, if done recursively, can lead to chaotic, unpredictable situations. And we know that nature is that way, right? Because every moment of nature takes the previous moment situation, changes it into another moment, and it's a series of these transformations. So that means even if nature was mechanistic, it would become chaotic and unpredictable. But the thing is, we keep looking down because sometimes chaos can just be, you can hear static. A broadband radio could hear static, where if you get narrow bands, you're really tuning out stations. You can find that there is order in there. And so we look closer and closer to see where there's order and where there's not order, and order sort of disappears and things get chaotic, and then we see the order again, and then it gets chaotic. Right now at the bottom of where we've gotten, it's at a chaotic point, and it doesn't look like it's going to come back to the kind of order we've been expecting. The reason I say that is, yes, with the two-slit experiment, we see that the chaos, the probabilistic nature of things, for one object, can have two physical locations. Its actual probability shows up as a material effect, and therefore it looks like at the bottom we're going to have things that fill probabilistic curves. Because that's the thing, when something is chaotic, there's a sort of sublime uniformity to it. We think of it, oh, it's changing. But no, see that center line of pixels or tiles or whatever in the center cell in Rule 30, it follows this random pattern. But overall, it's always 50-50, like flipping a coin. It's like there's a sublime uniformity in its lack of bias, one way or another. So I think when you take the quantum into it, quantum is a cellular kind of a thing. And this guy's a particle physicist. It's not a coincidence. And he points out that if quantum mechanics is told in terms of the cellular automata, it's not going to be squares butting up against each other. It's going to be more like some sort of essential particle, and space is all together, and we're all really in the same space anyway, and what seems like space is more a spatial quantum relationship that could be executed at any point in time. But anyway, okay. I'm curious if people have input on this. I was surprised people brought it up, so let's talk about it.